Hello guys. So I've created this short, well, not so short, maybe videos to cover what we're missing on astrophysics for a higher level. So this presentation will only cover those topics, and you can refer to it as many times as you want. It will be available here for you to check. Um, okay, so the topics that we're going to cover mainly are two. One is something called stellar processes, and we're going to go a little bit deeper into how stars produce their light and the reactions that happen inside stars in more detail, because we previously mentioned that, but we're going to go a little bit deeper into that. And then after that we have something called further cosmology, where again we're going to go a little bit deeper on some of the things that we talked about, the Big Bang and some of the implications of the accelerated expansion of the universe. So let's get started with this. The first thing that we're going to cover is called the Jeans criterion. It's actually a very simple complex. It can get really complicated, but we're not going to take it that far. So we know that stars form when a stellar cloud, like this one that you have here, is gathered by gravity, and the more mass is collected, the stronger gravity becomes, and then at some point that gravitational energy will be larger than the mean or average kinetic energy of the molecular gas. When that happens, the gas cloud, is set to collapse, and a protostar is formed. This concept of protostar is that first stage where the gas cloud has collapsed, but it's not doing fusion still yet. So if the mass of the cloud is m, then the protostar will be formed when that mass exceeds the Jeans criterion mass, which we call mj for obvious reasons. This limit, we don't have a number for that. We don't need to memorize any number for that. In that sense is different from the Chandrasekhar and the Oppenheimer-Volkoff limit. Because it has no specific number that we need to memorize. We just need to know that if the mass of the gas cloud exceeds this value, then the gravitational potential energy will be larger than the average kinetic energy of the molecules of the gas. So when that happens, it's like the gravitational attraction overcomes the tendency that the gas has to expand, and in that case the gas cloud will collapse and it starts to go along the path of forming a star. So that's what the Jeans criterion is, and everything that you need to know is that if the mass is larger than that, then the protostar is formed. Going to stellar evolution, and basically what we're doing here is we're looking at the same process of how stars are formed from the gas cloud. We're just giving this extra information that there's this thing called the Jeans criterion, and then after we guarantee that we're above the Jeans criterion, then we go into the process of forming the star. What I've added here is some part of what we had discussed in the presentation that we did with everyone, and we said then that when the gravitational attraction exceeds the average kinetic energy of the molecular gas, the gas cloud collapses. Now we have given that a name, and we know that that's the Jeans criterion, and that happens for cool stars between 10 and 100 Kelvin with enough mass. And again, now we know that that mass is the Jeans criterion. When the temperature is high enough, then light, visible light is emitted, a protostar is formed, and then when it's when it gets hotter and hotter and there's more pressure and the temperature goes around 10 to 7 Kelvin, fusion of hydrogen is produced and we reach the main sequence. Now, we've given a little bit of detail of how the gas cloud can evolve into a protostar, and now we're going to go into the details of how the how the fusion happens inside the stars. So, the base of nuclear fusion is this, it's actually three reactions are in the core of that process. Most people would say that it's just hydrogen turning into helium, but it's a little bit more complicated than that, and that was like the simplification that we did when we studied it all together. We just said that hydrogen transforms or fuses into helium, but the details are this. So the first step of the process is this one, where hydrogen nuclei will fuse to form deuterium nuclei. This atom here, or this nucleus here, is just an isotope of hydrogen. It's a heavy form of hydrogen, and then in the process electrons and neutrinos will be formed. The next reaction that we need to understand is the fusion of hydrogen with deuterium, which will produce helium-3, which is a heavy form of helium. In that process, photons will be released. And the third reaction that we need to understand is the actual fusion of helium-3 to form helium-4. And also in this reaction there's a product of two hydrogen atoms. These two hydrogen atoms will be very important when we're like trying to summarize what the whole reaction is. So if you look at this, actually what happens is not that hydrogen fuses to form helium, but that helium-3 fuses to form helium-4, and that helium-3 comes from the fusion of deuterium and hydrogen, and that deuterium comes from the fusion of hydrogen. So again, you can start to see how what we said before was a simplification of the whole process. So let's look at how this looks overall, and to kind of put together the whole equation for the synthesis of helium in stars. So somewhere in the star we have hydrogen atoms here, right? And well, this thing looks like could be modeling an atom, but it's not. So these hydrogen atoms are somewhere in the star. These other hydrogen atoms again are somewhere in the star. The star is big enough to have enough hydrogen atoms for this to be happening billions of times every day, trillions of times a day. So the first reaction will happen. Hydrogen will fuse into deuterium, producing electrons and neutrinos. And as a consequence, some of those nuclei, deuterium nuclei, will be floating around the star because they were produced by this reaction, and then those deuterium atoms will actually be able, given that there's enough temperature and pressure, they will be able to fuse with some of the other hydrogen atoms that there are around the star. Remember, there's plenty of that. So this reaction could happen anytime, given that this deuterium has been produced, and when that happens, then the helium-3 will be produced, and again this helium-3 will be wandering around the star, and eventually some of those helium-3 nuclei under the right conditions of temperature and pressure will meet and will come close enough to actually trigger the fusion of those two into helium-4, which is the desired last product. Now if you look at this, there's 1, 2, 3, 4, 5, and 6 hydrogen atoms that have been used for this whole reaction to happen. That's like the input that you're having. I'm not counting this as input because it comes from a previous reaction. So this 6 hydrogen nuclei here are like the input, the investment that you're doing for the whole reaction to happen. And at the end of the whole process, you're getting 2 of them back in a way. It's not that these 2 are coming back to you, but 2 are produced. So if you look at your net investment, it wasn't 6, it was 4, because you have 6 at the beginning that you put, and then 2 that are produced in the process, which leaves you at the end with a summarized reaction where 4, well, I'm not going to say that the reaction is just like this, but in this summarized version it looks like 4 hydrogen nuclei are fusing to form 1 helium nucleus plus 2 electrons plus 2 positrons plus 2 neutrinos plus a photon. So you can see how the overall process is, it matches what we had said before. And you can check like conservation of charge here. You can check conservation of mass. These are actually positrons, so sorry I said that they were electrons, but if you check then you're gonna see that you're gonna see that the charge initially is 4 because it comes from 4 hydrogen protons, and then after we have 2 from the helium and 2 from the positrons produced. So you have charge conservation, you have mass conservation also if you look at the number at the top. So this is the reaction that happens. Now, how much of this do you need to remember? Actually, you don't need to remember any of these reactions, but you need to be able to, given that you're reminded of these 3 reactions, you could be expected to indicate or to outline in general how the reaction happens, which is basically this process. So knowing this and knowing how those 3 reactions come together, you could come up with an explanation of this last one. Okay. Okay. So now, after hydrogen is fused, more elements are fused. Sorry for that. The hydrogen in the star will eventually be depleted, or well, not completely depleted, but the amount of hydrogen in the star will go down, and that will make it difficult for the star to keep fusing hydrogen. And remember, the star is always having this kind of battle between radiation pressure and gravitational pressure. So the star needs to look for new elements to fuse, and that's what happens when it runs out of hydrogen. As the gravitational contraction or gravitational pressure squeezes the star and makes it hotter, the star will get the energy to actually fuse heavier elements, and that will release energy that will help it keep its balance. So the whole process involves the fusion of heavier elements, and it will stop when iron is produced. Actually, the last element that is fused is silicon, and the fusion of silicon, we will see, produces iron as one of its processes. The helium fusion, and this is something that you need to remember, is produced through something called the triple alpha process, because if you look at this equation here, it involves 3 alpha particles, that is 3 helium nuclei. So remember, 2 protons, 2 neutrons. So 2 of them will react to produce beryllium-8, and then 1 beryllium-8 will react with 1 more of those to produce carbon-12 plus radiation. So this triple alpha process, we need to remember it. And we don't need to remember the equation, but you just need to remember that the triple alpha process is responsible for the fusion of helium into carbon. It's not difficult to remember the reaction, because it makes sense that helium goes into beryllium if you look at the mass numbers. So 4 goes to 8 and 4 goes to 12, so that's going to be easy to remember. So the sequence continues, and heavier, increasingly heavier elements will be fused, and that sequence sorry, is something that we need to keep in mind, particularly the steps leading from helium to carbon, neon, oxygen, and silicon. That sequence of elements is something that you need to keep in mind. So when they talk about elements beyond hydrogen, or beyond helium in the fusion inside stars, we're talking about this sequence, the fusion of after the fusion of hydrogen, we have the fusion of helium, then the fusion of carbon, neon, oxygen, and silicon. Each one of those requires a slightly different temperature. And well, unfortunately, you need to be aware of those orders of magnitude. So these are numbers that you're going to have to remember. And well, given that you know the sequence, again, the sequence is helium, carbon, neon, oxygen, silicon. The orders of magnitude will not be too difficult to remember. Now I need to clarify here, if you look at this sequence from helium, carbon, neon, oxygen, silicon, I'm not including beryllium, because beryllium is kind of in between, right? It's not that beryllium stays there for long, but it will be converted by completing the triple alpha process with this third alpha particle will be fused into carbon. So that's why we don't have an element that is being fused here, because this reaction, you wouldn't call it fusion as much as this one, because this one is actually fusing two of the same to form a third one. Now the numbers that you need to remember for helium, 1 times 10 to the power of 8. The first two, helium and carbon, are in the same order of magnitude, 10 to the power of 8, so that'll be easy to remember. And then the other three are in the order of magnitude 9. So neon, oxygen, and there you go, silicon will be in the in the ninth order of magnitude. So I don't know. For me, I just happen to remember that the first two are 10 to the power of 8, and the rest are 10 to the power of 9. Probably you have some type of way to remember this that makes more sense. But just those numbers will go with the sequence that we've repeated a number of times already. Helium, carbon, neon, oxygen, silicon. The powers will be 10 to the 8, 10 to the 8, 10 to the 9, 10 to the 9, 10 to the 9. And well, the coefficients of those, so this 1, this 6, this 1, you don't need to get those details. It's enough if you know that obviously carbon has a higher temperature, but they're both in the order of magnitude of 10 to the power of 8. I've included here the elements that are produced in that process, just as an indication of where some of the things that we see around us come from. So you can see how in the fusion of helium, carbon and oxygen are produced, and then in the fusion of carbon, elements like magnesium and sodium are produced. In the fusion of neon, we have more magnesium and so on. Sorry. And maybe it's the fusion of silicon that actually gives you the largest amount or variety of elements produced. So what do you need to remember from this slide? Triple alpha process, those three alpha particles fusing, first two of them together to form beryllium, and then one of them fusing with beryllium to form carbon. The sequence, helium after hydrogen, obviously helium, carbon, neon, oxygen, silicon, and the corresponding changes in temperature or the magnitudes of temperature that you need. Okay, that leaves you with a star, a red giant or a red supergiant, where this is the structure. Remember, all this happens only for red giants or red supergiants because this is all triggered after they run out of hydrogen. So this whole process will happen only for them. For red giants, you will only fuse up to carbon, right? Not anything heavier than that in general, and it's red supergiants that will give you the rest of the elements from oxygen up to nickel and iron. So this is the structure of the star. The heavier elements are accumulating in the center. Obviously they're heavier, so they're gonna be buried sorry, down in the center of the star. And then as you progress or you move out of the core of the star, you're gonna find layers where the lighter elements are being fused. So if you look for a fusion of, I don't know, neon, for example, that fusion of neon will happen right here in this third layer that we're mentioning here, and that's where the other elements are being fused. Okay, nucleosynthesis beyond iron. So what happens beyond iron? We know that when we reach iron, then fusion stops, and if fusion stops, the star has a big problem because it has nothing to stop gravity from making it collapse. So it will have only one option, and it is to go supernova. So how are those elements heavier than iron synthesized? Basically, what we need is a supernova explosion. Supernova explosions can be of two types, type 1a and type 2. We already talked about type 1a, and we said that type 1a supernovae are stars that were not supposed to go supernova. They were beyond the they were below the Chandrasekhar limit, and because they were in orbit around a larger companion, they started stealing mass from it, and then they reached the Chandrasekhar limit. And because we know exactly how much mass they have, which would be around 1.4 solar masses, then we know how much energy they release, and that's why we can use them as a standard candles. So this little table here is giving you a comparison between type 1a and type 2 supernovae. So let's go very quickly over type 1a. Evolves from white dwarfs that gain mass from a neighbor star. They release energy from fusion of heavier elements. They synthesize few elements heavier than iron, and the reason is why, because they have just reached the Chandrasekhar limit. They don't have as much energy, let's say, so the explosion is not as violent. But that's a good thing, because given that we know the mass that they have, because they just reached the 1.4 solar masses limit, then we can use them as standard candles, which is the fourth property. 1, 2, 3, 4, yep. And the fifth one is that the luminosity decreases faster than type 2 supernovae. Type 2 supernovae evolve from more massive stars, so stars that don't go white dwarf, but they go straight into supernova. They release energy from the shock wave that bounces off the incompressible neutron core. Sorry for the spelling of neutron here with that weird thing. That's because my autocorrect spelled it in Spanish. In Spanish we call it neutron. Anyway, so yeah, they release more energy. There's a more violent compression of the star, so that shock wave releases way more energy, and it will synthesize most elements heavier than iron. So when you look at things that are heavier than iron, they come from type 2 supernovae. When you're looking at well, sorry, let me say it this way. When you look at elements beyond iron or heavier than iron, most of them were synthesized in type 2 supernovae, and some of them were synthesized in type 1a supernovae only because this type 2 obviously has more energy to cause the ripping apart of the nucleus and to generate the processes that form heavier elements that we're going to see in the next slide. They are not used as standard candles, mainly because we just don't know what mass they have. So if we don't know the mass, we can't know how much energy they're emitting, and if we don't know the energy, then we don't know their luminosity. And if we don't know the luminosity, then we cannot use them as standard candles. And the luminosity decrease is slower than type 1a supernovae. So what do you need to know about this? That there's two types. You need to know these main differences. The most important ones will be these ones referring to the fact that one is standard candle and the other one isn't. One of them synthesizes most that most elements beyond iron come from one and not so many from the other, and where they come from, right? So it's not that you don't need to remember the rest of them, but if you were to memorize three things, I would go for the first one, the third one, and the fourth one. Good. Now let's see how that happens. So exactly how are those elements heavier than iron, like titanium, calcium, sorry, let me go back. How are those elements heavier than iron that are not in this list synthesized? They are formed through a process called neutron capture. Neutron capture is a process where you take an atom and you just stuff it with neutrons, right? It's like you take an atom and you force it to absorb a lot of neutrons, and depending on how many neutrons you force the atom to absorb, you can form heavier or lighter elements. So basically neutron capture is just that, an atom that is being forced to absorb a lot of neutrons, and it becomes heavier and heavier and heavier, and in becoming heavier it becomes unstable, and in becoming unstable it's more likely to decay and form other elements. So when the temperature of the core exceeds 10 to the 9 Kelvin, then the nucleus is collapsing, the energy has disintegrated the nucleus, and what we have is a neutron-enriched environment. So we have an environment where neutrons are just flying around at amazingly high speeds. And if you're an atom and you happen to be around, you're gonna end up being forced to absorb many of those neutrons. That process can happen in two ways, what we call the S capture. S stands for slow, and the R capture. R stands for rapid. The rate of bombarding of neutrons is slower than the half-life of the isotopes produced by the capture in slow capture. What does this mean? You need to remember that when a nucleus decays, it releases some of that instability that is a product of having gained too many neutrons. So suppose that you have an element in the nucleus of a star, and you bombard that with neutrons. So if you keep bombarding it with neutrons before you give it time to decay, you will make it bigger and bigger and bigger. But if you bombard it at a slightly lower rate, you will give it time to decay, and that's what happens in slow capture. The rate of bombarding is slower than the half-life of isotopes. So actually when they are bombarded and they produce other elements by gaining those nutrients and decaying, they have the time to do so. They're not forced to keep, absorbing more and more nutrients. So they can just go ahead and decay and produce some elements, and maybe later they will reabsorb or absorb more nutrients, and they can go through the process again. But in general, it's like they're given space, and more than space, time to decay. The isotopes produced don't have enough time to absorb too many nutrients, so they produce elements that are not that heavy, right? This is the slow capture is the process by which the elements that are heavier than iron but not too much heavier are going to be produced. Now the rapid capture is the completely opposite scenario, where the rate of bombarding neutrons is much faster than the half-life of the isotopes. So you are bombarded as an atom, you are bombarded, you want to decay, but before you have the time to decay, another neutron comes and hits you in the face, and you're forced to absorb it. And then you still want to decay, but it's like they never let you decay, and they just keep stuffing you with more and more neutrons, which will obviously produce super heavy elements, and those super heavy elements are the ones that are going to eventually decay into the heaviest elements of the periodic table, and that's where those elements come from. The rapid capture happens in type 2 supernovae conditions, because obviously that's where the most violent type of explosion, and the slow capture will happen for type 1a supernovae conditions. So that will be the slowest type of capture. Okay, so what you need to know obviously is how these two are different, and how the slow capture produces lighter elements, and the R capture or rapid capture produces heavier elements. The main reason being how the rate of bombardment compares to the half-life of the elements that are being formed. If it's faster, then you don't give time for them to decay, and they just keep being stuffed with nutrients, and more and heavier elements are produced. And if the rate is slower, then you give them time to decay, and they can actually kind of chill, decay, and wait a little bit until they get their next neutron. Okay, and that's it. So that's pretty much it. I don't know how long this has been. I haven't checked how much time I've been talking, but that's what covers the whole topic of stellar evolution. Remember, we're talking about some additions to things that we already knew. The first addition is the criterion for that gas cloud to actually start walking the path of becoming a star, and that first process is when it becomes a protostar if it exceeds the Jeans criterion. Then the next addition we made was what are the elements that we were missing about this summarized equation that we had given for nuclear fusion, and we know now where it comes from. It comes from those three main reactions that happen inside the star. Then we know what happens beyond hydrogen fusion. We know the sequence: helium, carbon, neon, oxygen, silicon, with the triple alpha process playing an important role in the fusion of helium, and the corresponding temperatures for the fusion of heavier elements. The corresponding consequence that this has on the structure of red giants and red supergiants. The main difference between type 1a and type 2 supernovae, how one is standard candle, the other one isn't, how they evolve from different types of stars. They both are supernovae, but they have very different origins, and they behave actually different. One of them being more violent than the other, type 2 being the most violent one. And obviously the consequences that has on the rate at which those elements will be bombarded and stuffed with neutrons, so they can create what you see around you. That's it. So the last slide of this section will be, I'm going to upload a short video maybe on this, because this is a mathematical process that I want you to look at. So keep an eye for that second video. We'll put it in ManageBack. And that's it. Next class, we're going to go over the further cosmology section. It's really nice, it's really interesting, and I think you're gonna enjoy like learning about those topics. That's it. So I'll see you around. Be safe. Don't get the virus. And if you get it, don't come to school or close to me.